light management and photovoltaic performance. The photovoltaic external quantum efficiency is the essential quantity that determines the efficiency of the solar cell, in particular with respect to the photocurrent, and it has two components: the light harvesting efficiency and the internal quantum efficiency. The internal quantum efficiency indicates for the photogenerated carriers if they are going to be collected at the contact by diffusion or other mechanism, and the light harvesting efficiency basically is the absorptance. So how many photons are absorbed from those arriving to the surface of the solar cell. The conversion of the incoming light into electrical carriers is an essential component of the efficiency, and to increase this, there are two main strategies. One is to modify the propagation of the photons such that absorption probability is increased. And this is the one we will describe in the following. The second possibility is to modify the spectral properties of the incoming light to a more favorable distribution, for example, the high energy photons, to break them into two smaller energy photons by down conversion. The light absorption depends strongly on the absorption properties of the materials, and this can be quantified by the absorption coefficient. Here we can see that lead-halide perovskite and gallium arsenide have high absorption coefficients, and silicon has much lower absorption coefficient, so that in the first case, with a few hundred nanometers up to 1 micrometer, it is enough to absorb the solar spectrum. But for silicon, it is a much higher length needed. Here we use the Lambert-Beer law, which is a standard absorption that is exponential absorption with respect to the thickness. This is the amount of the photocurrent that is lost. So that it would be needed like 1 millimeter to absorb the whole spectrum by silicon. But by the schemes we are going to discuss, the current thickness of silicon is about 180 micrometers. So the critical consideration is that the light needs a certain length to be absorbed. Otherwise, it would leave the absorber without being absorbed. Therefore, a simple back mirror multiplies by 2 the pathway of the light, but still this is going out of the solar cell, so that we use schemes for randomizing the reflection, and then this increases notably the pathway of the light, and then the probability that the photon is converted into an electron-hole pair of carriers. The standard way of randomizing is to use a Lambertian surface. This can be done in different ways, but in the end, the Lambertian surface totally randomizes the light by an emission pattern that is proportional to the angle with respect to the vertical. So when using a scattering layer, the light is randomized, and then this reduces the probability of the escape, and the density of rise of light inside the solar cells increases, and this light trapping scheme increases by a factor for n squared, which is where n is the refractive index of the material, and this is called the Jablonowicz limit. This is the scheme for a pyramidal texture of the surface of silicon, for a randomized and an anti-reflective coating, for enhancing the penetration of the light and minimizing the escape of the light, and also improving a surface perturbation to reduce recombination. Here is a different configuration, which is the interdigitated back contact silicon solar cell, where the two selective contacts for electrons and holes are in the backside. In this way, the surface loses opacity due to the contact extractor. And this is also interesting to remark that the p-n junction cannot be in the middle of the solar cell, because in this case, the p and n structures are both in the backside. We have already remarked before that achieving the radiative limit of the VOC requires a good efficiency of light emission. When the light emission capability of the solar cell working as an halide decreases, then the VOC decreases. And this has been emphasized also by Jablonowicz and co-workers. If the internal quantum efficiency decreases, then the overall efficiency decreases. In general, having a high luminescence efficiency is an indicator that you have a high density of electrons inside the solar cell at a given incoming light intensity, so this indicates a good efficiency. So that when the recombination and the electronic quality has been made very good to avoid the recombination losses, then schemes of light extraction have to be used to improve the obeyance of the tail balance and increase the efficiency of the solar cell. One effect that is important at these very high efficiency levels is the photon recycling. This means that when there is a radiative recombination event, the photon might not reach the surface. It can be absorbed again, but if the non-radiative recombination rate is very small, then it will be re-radiated. In the end, the photon goes several events of absorption and emission, and this enhances the probability that is emitted. So that this is a diffusion process of the photons between different capture events. As we mentioned before, this will enhance the density of carriers inside the solar cells and directly enhance the VOC and the efficiency by this internal photon diffusion. The photon recycling can be measured or estimated by irradiating a structure on one side and measuring the emission at the other. So this will depend on the illumination flux and depend also on the thickness of the layer, and the emission, depending on these factors, indicates that the effective recombination lifetime is not a constant anymore, but depends on the flux and on the size. It's a waveguide structure where we insert a primary set of photons, and they are going to do photon recycling. So they are going to be the secondary photons generated at a specific range of frequencies. This will change the spectral composition of the light inside the guide.